Next, we're going to build a more refined model. So we don't have too many warehouses that we've sucked all the air out of. So we're going to consider drag this time. So we're going to assume we have an object with mass m that's falling freely. And it's very common to model air resistance as proportional to our velocity. So air resistance also gets called drag. This is going to be opposing the motion. And so if gravity is pulling us down, the drag is going to be in the opposite direction of that motion. Okay. So let's take a look at what we have in terms of constants. So constants, we have mass. Oh, let's write down the forces we see. So we have the force of gravity, which was given by mass times the gravity constant. We also have the drag force, which is going to be pointed in the opposite direction of our velocity. And so we said this was proportional to velocity, but it's going the opposite way. So we're going to use gamma as our constant and a positive constant, and we'll put a negative sign out front to say, okay, we're opposing velocity. Okay. All right, we're going to also have variable v. That's going to be our velocity in meters per second. And t is going to be the time in seconds. And t, of course, is our independent variable. Okay, so let us take a look. We're going to use that same underlying principle of Newton's second law that says that the sum of the forces, the net force on the object, is equal to the mass times acceleration of the object. Okay, and so what are the forces acting on this object? We have mass times the gravity constant, and we have the drag constant, the drag force, so minus gamma v. And this is going to be equal to mass times our acceleration. Remember, acceleration here is dv dt. Oops. Okay. All right, let's take a quick look at our at this equation. Notice we can leave it in this format, or we can divide through by mass. This gives us dv dt equals g minus gamma over m times v. And since we often use the just 9.8 for our gravity constant, we've got 9.8 minus gamma over m times v. Okay. All right. So if we want to take a look at this model, let's see what it says. So let's think a little bit about what our slope field is going to look like. So we see here that we have this linear function. Okay, so and the slope in front of the v is negative. Okay, so what we can see here is that so without setting values for gamma and m, we can still get a sense for what's going to be happening. Okay, so when v is small, if we start out close to 0, notice that we're going to have positive slope, that it's going to be looking like our velocity has a rate of change close to 9.8. So we're going to have these positive slopes. Okay. Now, as this increases, as v increases, our slope is going to be getting smaller until at some point we're going to have a slope of 0. We can solve when that happens. We're going to have dv dt equals 0 when we have 9.8 minus gamma over m times v. So moving this over, we have gamma over mv equals 9.8. So when v is 9.8 times m over this drag coefficient gamma, then we're going to have no change in our velocity. Okay. This is going to correspond to what's called So this is called the terminal velocity. And if we had started off any higher velocity than this, what we're going to find is that we have negative slopes. Okay. Notice this equation, this differential equation, does not depend on time. It only just depends on the velocity that we're going. Okay. So whatever our picture is at t equals 0, we can just repeat it. And what we're going to find for our solutions is that no matter where we start, our solutions are going to be approaching this terminal velocity. Okay, so there's some limit on how fast we're able to fall. That it's going to depend both on the mass and the drag coefficient. So, and we can see how it's going to depend on that. If we look at this equation, we see that if our mass is smaller, that our terminal velocity is going to be smaller as well. If our mass is larger, then our terminal velocity is going to be bigger. Okay, cool. And if we had thrown it at exactly the terminal velocity, it'll just stay with that velocity for all time. Okay. Next up, we're going to look at Newton's law of cooling.